All right, we're going to start talking about quantum theory, which is something we did talk about last year. It's the stuff that talks about orbitals, the S, the P, the D, parts like that. And really what this helps us explain is things like light. Light and color can both be explained due to the movement of electrons and kind of their placement around a particular atom. So to really understand quantum theory, we first need to talk about waves, and waves are what make up electrons and light and color. So the components of a wave. If you look at a wave, and we've seen them before in physical science, so a wave moves up and down, a transverse wave like this, and so this string would be moving, and we would see the motion of energy going up and down. The wavelength is the distance between two successive peaks on a wave. It can be like they have it drawn right here as the top, so those are the crests. You can also measure the wavelength as that distance right there. It should be exactly the same, as long as it's two successive points. So like you couldn't measure from there to here, because those 2 points are not successive or straight across from each other. Then there is wave frequency. This one's harder to visualize just looking at pictures, because frequency deals with kind of the motion of the wave. And so let's just imagine this is kind of a time-lapse video of a 1 second time period. So over 1 second we produced 2 peaks, and so the frequency there would be 2 peaks per second. So it would be 2 hertz then as the units. That would be a 2 hertz wave. A high frequency wave then, like this bottom one, we can see that if this is once again just a 1 second period, it had 1, 2, 3, 4, 5, 6, and so this would be a 6 hertz wave. And frequency is just how often or the number of times a wave repeats itself per second. So the more times that we get that repetition, the more higher frequency it is. And you can see a relationship here then between frequency and wavelength. So if you look at this low frequency wave, it has a high wavelength. So what that tells us then is as frequency goes down, wavelength goes up. We can see down here that as the frequency went up, the wavelength went down. So you get shorter wavelengths with higher frequency, longer wavelengths with lower frequency. So that's what we call an inverse relationship. As one goes up, the other one goes down. Remember that. That's an important fact. And actually the choice for colors that we see here, so this was red and this is violet, that's for a reason. What we see as the color red is actually a very low frequency wave, and so it would have a longer wavelength than violet, which would have a higher frequency. And so that's really what our brains interpret as colors. Colors are not an actual thing. It's our brain's interpretation of a particular wave. So when we see a longer wavelength, light wave, we see it as red. When we see a higher frequency wavelength, we see it as violet. And then in between you get the different colors. So the change in frequency, the change in wavelength is what gives us changes in color. Which is kind of crazy to think about. So different colors. Look at something in your room right now that has color on it. That color, it's not a real thing. It's really just a wave of light shining or reflecting off of that object. And the frequency of that wave shining off there is being sent to your brain. Your brain is processing that signal and turning it into a color. Just like the radio that might be sitting on your counter. When you turn that on, it's picking up radio waves and converting them into sound. Your eyes are converting light waves into color. All right, here is the equation. So the speed of light through a vacuum it's a universal constant, 3 times 10 to the 8th meters per second. All right, and that anytime you see C, you can use that number right there. So you don't need to really ever think about that. Remember this number, okay, and you'll know what C is. It changes, in a vacuum it's 3 times 10 to the 8th. When it's not in a vacuum, it might be like 2.99999 times 10 to the 8th. So it's not going to affect it that much. We can use it as a universal constant, so it's always the same. Wavelength is the distance between those successive peaks or troughs. To note, wavelength must be in meters. The reason it has to be in meters is because the speed of light is in meters. So I've told you guys it is extremely important that you put units on everything. All right? Units are just another form of equation, and we have to make sure that they match up. If they do not, that is a great indicator that your equation is wrong. And then the frequency is seconds inverse, so it's how many times something happens per second. So it's peaks per second, which means it's the same thing as seconds inverse, or 1 over seconds. We shorten that to hertz, is what we end up calling that. So 1 over seconds is the same thing as hertz. So then, what you guys should notice here then is if we look at this equation, we can think of it just in terms of units. So meters per second is the speed of light, and then wavelength is meters, and frequency is 1 over seconds. And so, really, meters times 1 over seconds is meters per second. Where this is tricky is frequency of light. Okay, think a meter is like a yard. It's like 3 feet long. We don't measure light waves in meters. That's way too big. So typically, you're going to be given measurements in nanometers. So you need to be ready to make that conversion from nanometers into meters so that you can use this equation. And that is why it is really important that you write units on everything. All right, if you find something in your room right now that's green, a green object is reflecting light, and it's reflecting it with a frequency of about 545 nanometers. Depending on the shade of green, it might be a little less or a little bit more than that. So we want to find the frequency, and we're going to be using, of course, the equation that we just looked at, which is the speed of light is equal to lambda, which we use to symbolize the wavelength, and then the frequency, which is v. That's also something tricky. So v, you might think velocity. It's not. It stands for frequency. So in this case, we are going to solve for frequency. Something I recommend is rearrange your equation before you plug numbers in. It'll help you out to do that. So then we can solve this for frequency as c divided by lambda. So that's just the equation rearranged. Now we can plug in some numbers. So frequency would equal c. What's c? It doesn't tell us in the equation. Oh, that's right, c is a universal constant. It's always 3.00 times 10 to the 8th, or just 3 times 10 to the 8th. Okay, but we want sig fig, so we'll put it with 3, and that's meters per second. All right, the wavelength is 545 nanometers, so now we can solve. Oh, what's that you say? We can't solve yet because we have nanometers here and meters up there. You are absolutely correct. Since we wrote down units just like we're supposed to, we caught that mistake. And we can see that nanometers will not cancel out meters, so we need to put that into meters. All right, and 1 nanometer is equal to 10 to the negative 9th meters. And so we're just going to end up, you can lay down the stoichiometry if you want to, but we're going to multiply 545 by 10 to the negative 9th. And so we can just rewrite this as 545 times 10 to the negative 9th meters. And there's our conversion right there. All right, so 545 times 10 to the negative 9th. That looks like an inequality sign. There we go. Now we can see that meters will cancel out meters. The units that we are left with is 1 over seconds. So this would be equal to 1 over seconds, which is also known as seconds inverse, which is also known as hertz. So even without plugging any numbers in, we can see that our answer is at least, or equation is at least set up right because we wound up with the units that we should end up with. And then when we do divide those two, we find out that the frequency is 5.50 times 10 to the 14th. So 5.50 times 10 to the 14th times per second. So a lot of times per second for this particular wave. Okay, so it's not a complicated equation, but just put your units on everything. Naked numbers, they're embarrassing for everybody because you make mistakes and they make me blush. So just make sure you put units on everything, your answers, all of your equations, and then show that they cancel each other out just to verify it for yourself. You can solve, I'd say, over half of your mistakes just by writing units on there. So light and the electromagnetic spectrum, as it's referred to, this entire list, electromagnetic spectrum, it's really a spectrum of light, and it's continuous. What that means is there's no clear distinction from one place to the other. And you can see that really good from this color chart right here. So look how it just continuously flows from one color to the other. So where does blue start and green end? Well, somewhere in there, but there's not really like a line that marks this is blue, this is green. It's a continuous spectrum, so it flows from one to the next. And that's because they're light waves. And so light waves, you can gradually increase the wavelength or decrease the frequency. And we can see as we go across the spectrum that the wavelength is increasing. And if wavelength is increasing, that means that the frequency is decreasing. And so we're getting lower and lower frequencies as we come towards red. And so, if you think of this just as a knob that you're slowly turning up, so you're slowly increasing that wavelength, you can see how it's getting more and more stronger, and we just change from one to the other. So this is a continual spectrum. And also tied in with that, this is just a very small range that we can actually see. So this is just the area that our brains can interpret. There's other forms of waves out there, and they're made of the same thing. It's just energy in these waves coming through. UV and infrared, we can't see those, but they're out there, and they're made of the same thing as colors. X-rays, microwaves, radio waves, X-rays, or gamma rays, all composed of the same thing. It's just an increase in the wavelength that makes it turn from one thing to the other. There's no breaks, just one color, one thing fades from one and gently transitions into the other.